So here's the math portion of my lecture on the golden ratio. As promised, I'm going to show you that to construct a pentagram, you need to be able to construct a golden segment. So if you imagine that this is a perfect pentagram, we want to try to figure out let's look at these triangles. What can we figure out about them? Well, let's start with this pentagon in the middle. We know that this is a regular pentagon, and in a pentagon, you have 1, 2, 3, 4, 5 congruent angles. Now, it's a theorem in geometry that if you have a polygon with n sides, then the sum of the interior angles is going to be 180 degrees plus the number of sides that you have minus 2 times 180 degrees. So what does that mean for a pentagon? So we've got 5 sides. So that means that the sum of our interior angles is 180 degrees plus 3 times 180 degrees. And that comes out to be 540 degrees. Now, to get each of these angles, we divide by 5. 540 degrees over 5 is equal to 108 degrees. So each of these interior angles is 108 degrees. Now, that means that this angle has to be 72 degrees. And so does this one, and this one, and this one, and this one, and that one. You get the point. All those triangles have a base angle of 72 degrees. So all of our triangles look like this. And they're isosceles. The reason we know that is if two sides of a triangle have the same length, then the angles opposite are going to have the same magnitude. And to get this third angle, we just take 180 degrees minus 2 times 72 degrees, which gives us 36 degrees. Let's call this length x and this length y. I want to try to find some way to express x over y. Now, here's where the trig comes in. I'm going to cut this triangle in half, and I'm going to look at this right triangle. So this is y over 2 because I cut that length in half, and that's x, and we know this is 72 degrees. So if we think back to the trig that we know, or if you don't know any trig, you can watch my trig primers. The cosine of 72 degrees is the adjacent, so y over 2 over x, and which simplifies a little bit to y over 2x. Now, I want to find x over y. So I'm going to multiply both sides of this equation by x over y. And then I'm going to divide both sides by cosine of 72 degrees. And so we get cancellation there and there. And so what we are ultimately left with is x over y is 1 over 2 cosine 72 degrees. So we're almost there, you would think. Because all we need to do now is figure out what the cosine of 72 degrees is. But as it turns out, that's actually a fairly fun and interesting but kind of complicated question to answer. So let's try to solve that. Let's try to find the value of that. And this is where the meat of this is going to be. This is why this is a separate video. So I'm going to let 5 theta be 90 degrees. And the reason why I'm doing that is going to be clear soon. But theta is going to be 18 degrees if we just divide both sides of that by 5. And so we can rewrite this as 2 theta plus 3 theta is 90 degrees, or 3 theta is 90 degrees minus 2 theta. So now let's take the sine of both sides. Sine of 3 theta is sine of 90 degrees minus 2 theta. So I didn't prove this identity in my trig video, but if you use the difference of arguments of a sine, then you get that the sine of 90 degrees minus 2 theta is cosine of 2 theta. Okay. But cosine of 2 theta, I did show, was 1 minus 2 sine squared theta. And it's the sine theta that I'm after here. The thing I don't have that I need is sine of 3 theta. So let's look at that. So sine of 3 theta is sine of theta plus 2 theta, which you can rewrite as sine theta cosine 2 theta plus cosine theta sine 2 theta. So let me rewrite my cosine 2 theta as 1 minus 2 sine squared theta. And then my cosine theta and my sine 2 theta I need to rewrite a little bit. So sine 2 theta, recall, is 2 sine theta cosine theta. And so we're left with this being sine theta minus 2 sine cubed theta plus 2 sine theta cosine theta times cosine theta, so we get a cosine squared. But using the Pythagorean identity, we have that 1 equals sine squared theta plus cosine squared theta. So cosine squared theta is 1 minus sine squared theta. And so I can do a little bit more rearranging of this. We get that plus 2 sine theta minus 2 sine cubed theta. So now we've got just sine thetas everywhere, and we get 3 sine theta minus 4 sine cubed theta. And if we go back, that is just the sine of 3 theta. So If I combine what I wrote up here and what I wrote down here, we get that 3 sine theta minus 4 sine cubed theta is equal to 1 minus 2 sine squared theta. Okay, so now I'm going to rewrite this equation by making the substitution x equals sine of theta. And this is primarily for convenience sake, so I don't have to write sine of theta every single time I need to refer to it. But also to make sure that that from this point on, nobody gets really stuck in the math. So we've got 3x minus 4x cubed is 1 minus 2x squared. If I move everything over to one side, we get 0 equals 4x cubed minus 2x squared minus 3x plus 1. So our problem is essentially boiled down to factoring a polynomial. Now, this polynomial is not necessarily so easy to factor, though. But there is one easy solution that we can find. If we add the coefficients of the polynomial together, it's the same as plugging in x equals 1. And what we end up with is we get 4 minus 2 minus 3 plus 1, and that's equal to 0, which tells us that x equals 1 is a solution. So let's try this solution and see if it makes sense. So we've got sine of theta equals 1. But sine of theta equals 1 only happens when theta is a certain type of angle. When it's 90 degrees plus a full circle or more. So that doesn't work because, recall, theta was 18 degrees. It certainly was not 90 degrees plus an integer multiple of 360. Let's factor out x minus 1 and see what else we're left with. Okay, so we have now reduced our problem to solving this equation. 4x squared plus 2x minus 1 equals 0. So let's solve it. Because this is a quadratic, which we know how to solve. So, just as a reminder, if you have got ax squared plus bx plus c equals 0, your solutions are going to be of this form. So we're going to apply that here. So we've got negative 2 plus or minus the square root of 2 squared minus 4 times 4 times negative 1 all over 2 times 4. So we get negative 2 plus or minus the square root of 4 plus 16 over 8. So we get negative 2 plus or minus the square root of 20 over 8. Now 20 can be written as 4 times 5. So when I take the square root of that, I can rewrite that as the square root of 4, square root of 5, and then the square root of 4 simplifies to 2. So we get negative 2 plus or minus 2 root 5 all over 8. And if I cancel a 2 from everywhere, we get negative 1 plus or minus the square root of 5 over 8 over 4. So we need to figure out which of these solutions we want. Recall that, again, x is sine of theta, sine of 18 degrees. Now this quantity is going to be a positive number. So, one of these is a positive number, one of them is a negative number. Let's look at negative 1 minus square root of 5 over 4. This quantity is negative, and this quantity is positive, so that means that's a negative number. So it's not the one that we want. So the one we want is negative 1 plus the square root of 5 over 4. Now, this relates to a special number that we've talked about before, but not necessarily super clearly. So what happens when I take 1 divided by that number? Well, let's multiply numerator and denominator by 4. We get 4 over negative 1 plus the square root of 5. And now here's a bit of a non-obvious thing to do. Let's multiply both our numerator and denominator by 1 plus the square root of 5. And the reason why will appear shortly. So our numerator becomes that. Our denominator, let's go ahead and FOIL this out. So we've got negative 1 plus the square root of 5 minus the square root of 5, and then plus the square root of 5 squared. Now this quantity is just 5. These two, if I add them together, I get 0. So the denominator becomes 4. And so we get 1 plus the square root of 5. But those of you that know what the golden ratio is, know that the golden ratio, phi, is 1 plus the square root of 5 over 2. And so this is equal to 2 times the golden ratio. Now, we found what sine of 18 degrees is. It's 2 times the golden ratio. Now, we haven't figured out what we wanted to figure out. Cosine of 72 degrees. But that's the same as the cosine of 90 degrees minus 18 degrees, which is the same as the sine of 18 degrees. So we have found cosine of 72 degrees. Now, why was it we were wanting the cosine of 72 degrees again? Let's see. Oh, yeah. Because it gave us this relationship for the side lengths of our triangle. So, by applying the value that we have now discovered, the ratio of the side lengths of our triangle is 1 over 2. Ooh. Sorry, there was a mistake back here. This is 2 phi, but that's not what x was. X was 1 over that. It was the original thing that we had. This. So, sine of 18 degrees was supposed to be 1 over 2 phi. And so cosine of 72 degrees is 1 over 2 phi. And so we get that, actually. Now our 2's here cancel. And then I can multiply numerator and denominator by phi. And we're left with just the golden ratio. How interesting. The long side of our golden triangle, divided by the short side, gives us a golden proportion. Certainly I didn't expect that the first time I saw this, but that shows that to construct a pentagram, you need to be able to construct a golden segment. That's part of why this number was so intriguing to the Greeks.